There's a specific kind of exhaustion that's worse than just being tired. It's the kind where you've been running on empty all day. Your eyes hurt, your focus is gone, your body feels heavy. You are genuinely, completely done. And then you get into bed, the one place you've been looking forward to all day, and nothing happens. Your brain doesn't turn off. It doesn't even slow down. You're lying there in the dark, exhausted, and your mind is running at full speed like it has somewhere to be. Most people assume this is just stress, or anxiety, or a personality thing. Some people are just wired to stay awake. But here's what's actually going on. Your brain has a dedicated neurological system, a specific cluster of neurons in the hypothalamus whose entire job is to switch you off at night and switch you on in the morning. Neuroscientists call it the ventrolateral preoptic nucleus, and it functions almost exactly like an electrical flip-flop switch. When it's working correctly, it shuts down every arousal system in your brain within minutes, drops your core body temperature, and keeps you locked in deep, restorative sleep. When something is blocking it, and most people are blocking it with things they do every single day, you get what we just described. Exhausted body, wired brain, lying awake in the dark. This switch is real. It is well researched, and Harvard researchers have literally turned it on with a laser in a laboratory and watched animals fall immediately into deep sleep. The question isn't whether this system exists. The question is what's getting in the way of yours and how to remove it. Let's start with the biology. The flip-flop inside your brain. Your brain doesn't gradually fade from awake to asleep like a dimmer switch. It flips, rapidly. The transition from full wakefulness to sleep is designed to be almost binary, a clean switch rather than a long, slow fade, because a half-awake, half-asleep brain is a functionally compromised brain. You need to be one or the other. The mechanism behind this is called a flip-flop circuit. It works through mutual inhibition, two opposing sides, each working to suppress the other. On one side, the ventrolateral preoptic nucleus, or VLPO. This is the sleep-promoting side. Neurons here produce two inhibitory chemicals, GABA and galanin, that act like biological off switches for every arousal system in the brain. When VLPO neurons fire, they reach across to the histamine system, the noradrenaline system, the serotonin system, and the orexin system, all the systems responsible for keeping you alert and conscious, and they systematically silence them, one by one. And when the arousal systems go quiet, you go to sleep. On the other side, the arousal systems, the most powerful of which is the orexin system in the lateral hypothalamus. Orexin neurons, when active, do the opposite. They excite every arousal center in the brain and simultaneously send inhibitory signals back to the VLPO, suppressing it. When orexin wins, the wake side dominates and you stay alert. Here's what makes this a flip-flop rather than a gradual transition. Both sides inhibit each other. Whichever side gains a slight advantage tips the whole system rapidly into one state. You go from awake to asleep quickly and from asleep to awake quickly, precisely because this isn't a slow gradient, it's a bistable system snapping between two positions. This explains something that many people find confusing about their own sleep. The moments just before falling asleep often feel rapid, almost like falling off a cliff into unconsciousness rather than a smooth descent. That's the flip-flop working correctly. The system switched. And the moments of lying awake for hours, tired but alert, that's a switch that's having trouble flipping, because the arousal side is being propped up by something that shouldn't be there. The Harvard Laser Study. In 2018, researchers at Harvard Medical School and Beth Israel Deaconess Medical Center ran an experiment that provided the clearest causal proof yet of how this system works. Using a technique called optogenetics, which involves engineering specific neurons to respond to light pulses, they targeted the galanin-expressing neurons in the VLPO of mice. When they stimulated these neurons at low frequency, between 1 and 4 pulses per second, the mice fell into deep sleep almost immediately. not gradually, within seconds of stimulation. Core body temperature dropped, slow-wave brain activity appeared. The animals were out. This was not sedation. This was the actual sleep machinery of the brain being activated directly. The VLPO fired. The arousal systems shut down. Sleep happened. There's one interesting footnote from this study. When researchers tried stimulating the same neurons at higher frequencies, around 10 pulses per second instead of 4, the effect reversed. The neurons experienced what's called conduction block, essentially a circuit overload where they stopped firing altogether. The result was wakefulness, not sleep. This matters beyond just being a technical curiosity. It shows that the VLPO isn't a system that responds to brute force. It works at its own pace, in its own rhythm. You can't force sleep by throwing more stimulation at the system. You have to allow the conditions under which it naturally fires, slow, quiet, low arousal, and let it do its job. Which brings us directly to the things that prevent it from doing that. Orexin, the system that won't let go. Before we get to what's disrupting the switch, it's worth understanding the main opponent on the other side of the flip-flop, because orexin is fascinating and its role explains a lot about why poor sleep feels the way it does. Orexin neurons in the lateral hypothalamus are active during wakefulness, particularly during purposeful, motivated activity. They excite every major arousal center in the brain simultaneously, keeping the whole system running in a coordinated, sustained state of alertness. And they project directly to suppress the VLPO, keeping the sleep side of the flip-flop firmly down. Think of orexin as a finger pressing one side of a seesaw. As long as it's pressing, the other side can't rise. The clearest evidence for what orexin actually does comes from what happens when it's gone. Narcolepsy, the condition characterized by sudden, involuntary sleep attacks during the day, episodes where people literally collapse mid-sentence or mid-laughter, is caused by the autoimmune destruction of around 90% of orexin neurons. Without orexin pressing down on the wake side, the flip-flop becomes unstable. The system shifts randomly between states. People fall asleep during conversations. Their muscle tone collapses during emotional moments, a symptom called cataplexy, because the REM sleep atonia system intrudes into wakefulness without warning. Narcolepsy is, in a very direct sense, what happens when the orexin stabilizer is removed from the circuit. Most people don't have narcolepsy, but the orexin system can become chronically overactivated in ways that push the wake side of the flip-flop too hard for the VLPO to overcome, through stress, through chronic stimulation, through the signals we'll get to shortly. The result isn't narcolepsy. It's a less dramatic but equally real version of flip-flop instability, a brain that can't fully commit to sleep, wakes easily, cycles through lighter stages all night, and produces that particular feeling of having technically slept without being restored. The pressure that builds the flip. Now, let's add the third player in this system, adenosine. Throughout the day, as your neurons fire and consume energy, they produce adenosine as a metabolic byproduct. Adenosine accumulates steadily in the brain, building what researchers call homeostatic sleep pressure. As this pressure rises, adenosine begins doing two things relevant to the flip-flop. It inhibits arousal neurons, weakening the wake side, and it excites VLPO neurons through adenosine A2A receptors, strengthening the sleep side. Over 16 or so hours of wakefulness, adenosine pressure reaches a level where the VLPO has a significant advantage. And if nothing is artificially propping up the arousal systems, no late caffeine, no bright blue light, no thermal interference, the flip-flop tips. VLPO fires. Arousal systems silence. Sleep begins. Caffeine, as most people know, blocks adenosine receptors. It doesn't reduce the adenosine, it just prevents the signal from reaching its targets. The pressure is still building, it's just not being read. When caffeine wears off, the backlogged signal hits all at once. That's the crash. And if caffeine is still partially active at bedtime, the VLPO is fighting for the flip-flop without its usual adenosine support, making sleep harder to initiate and lighter when it does occur. Here's something the Harvard VLPO research revealed that ties directly into practical everyday choices. When VLPO neurons were activated in those mouse studies, two things happened simultaneously. The mice fell into deep sleep, and their core body temperature dropped by several degrees. VLPO activation and body cooling are not just correlated, they are linked by the same circuit. The hypothalamus manages both. This means that for your VLPO to flip the switch effectively, your core body temperature needs to fall. And it needs help doing so. Your body temperature follows a natural daily arc, rising through the morning, peaking in the late afternoon, and beginning to decline in the evening. That decline is part of what biases the flip-flop toward sleep. But this system is exquisitely sensitive to interference. A warm bedroom resists the temperature drop. A heavy meal close to bedtime raises core temperature through digestive thermogenesis, the heat your body generates processing food, and keeps it elevated for hours. Intense exercise near bedtime raises temperature and cortisol. All of these push against the biological prerequisite for VLPO dominance. The good news is that this system can be worked with just as easily as it can be worked against. A warm bath or shower taken roughly 90 minutes before bed achieves something counterintuitive. The warm water dilates blood vessels near the skin, which releases heat from the body's core. When you get out, the surface of your body radiates heat rapidly and your core temperature drops, sometimes more quickly than it would have without the bath. You've essentially given the VLPO's thermal trigger a head start. Keeping your bedroom cool, somewhere around 60 to 67 degrees Fahrenheit or 15 to 19 Celsius, removes one of the most common physical barriers to the temperature drop your brain is waiting for before it commits to deep sleep. The three things. Shutting off your sleep switch. With the biology understood, let's talk directly about what modern life does to this system, because there are three specific interference patterns that appear consistently in the research. The first is artificial light after dark. Your suprachiasmatic nucleus, the master circadian clock in the hypothalamus, receives direct input from a specific type of cell in your retinas called intrinsically photosensitive retinal ganglion cells. These cells contain a photopigment called melanopsin that is acutely sensitive to blue wavelength light, roughly in the range of 460 to 480 nanometers. When this light hits those cells in the evening, it sends a signal to the SCN that reads as daytime. The SCN, believing it's still day, suppresses melatonin release from the pineal gland. Melatonin normally helps lower core body temperature and signals to the VLPO that night has arrived. Without that signal, the thermal trigger stalls. Arousal systems stay active longer than they should. The flip-flop stays on the wrong side. The light from a typical phone, tablet, or LED bulb in the evening is loaded with this exact wavelength. An hour of screen use at night can suppress melatonin for 2 to 3 hours. The SCN cannot distinguish between the sun and your phone. Both read as daytime through the same receptor. Dimming your environment after sunset, using warmer orange and red toned lighting, reducing screen brightness, or using blue light blocking glasses with strong amber lenses in the evening removes this interference and allows the natural sequence to unfold. Melatonin rises, core temperature drops, VLPO fires, arousal systems quiet. Morning bright light is the other half of this equation. Getting outside within 30 to 60 minutes of waking, exposing your eyes to natural daylight, sends a strong, clean signal to the SCN that anchors your circadian clock to the correct time. This does two things for your sleep. It triggers a sharp morning cortisol pulse that produces genuine daytime alertness, and it starts the countdown timer for melatonin onset roughly 12 to 16 hours later. The stronger and more precisely timed your morning light signal, the more reliable your evening melatonin rise will be. Morning light isn't just about waking up faster. It's about setting the conditions under which your sleep switch will fire that night. The second interference is eating too close to bedtime. The research here converges on a principle that most people know in the abstract but routinely ignore in practice. Your last significant meal should be finished at least 2 to 3 hours before sleep. This isn't arbitrary. Digestion activates the sympathetic nervous system, the same system that runs fight or flight arousal. It raises insulin, which interferes with the nighttime release of growth hormone that normally peaks during early deep sleep. It generates body heat that competes with the thermal drop the VLPO needs. And it sends the peripheral clocks in your liver, gut, and metabolic organs a signal that it's still feeding time, which misaligns them with the brain's sleep phase signal. Your body has a set of internal clocks distributed throughout its organs. These peripheral clocks are synchronized partly by the SCN, but also directly by meal timing. When you eat at 11 p.m., the liver clock reads one time while the brain clock reads another. That internal desynchrony affects hormonal balance, metabolic function, and the quality of the sleep that follows. Finishing meals earlier also lowers the likelihood of the blood sugar crash mechanism discussed in previous content, the one where a high glycemic dinner creates a glucose surge and subsequent reactive dip that triggers a cortisol response in the middle of the night. Clean blood sugar through the night removes one more signal that can tip the flip-flop back toward wakefulness at 2 a.m. The third interference is mechanical disruption during sleep itself. This one is less about the flip-flop and more about what happens once it's flipped. Once you're asleep, the VLPO needs to maintain its dominance. Any signal that crosses a certain arousal threshold can fire a brief reactivation of the wake side, a micro-arousal, that interrupts the sleep stage you're in without necessarily waking you fully. Physical discomfort is one of the most consistent sources of these micro-arousals. Spine misalignment that creates muscular strain throughout the night. Pillow height that doesn't support the head-neck angle, increasing pressure on the cervical spine. Sleeping positions that partially collapse the airway, particularly back sleeping in people with any degree of airway narrowing, which generates low-level respiratory effort that the brain registers as a stress signal. You may not experience these as wakings. You may not remember them at all. But if your deep sleep percentage on a wearable is consistently low, if you thrash or shift frequently, if you wake with neck or back stiffness, the mechanical picture is worth examining.
Neutral spinal alignment, which for most people means side sleeping with pillow height that keeps the head level with the spine and a pillow or cushion between the knees to prevent the top hip from pulling the spine into rotation, removes a persistent low-level stressor that the arousal system is continuously reacting to.
What's happening while the switch is on?
Understanding why protecting your sleep switch matters requires briefly looking at what's actually produced during the deep sleep it enables. Slow-wave sleep, deep non-REM sleep, is when your brain clears metabolic waste through the glymphatic system, including proteins associated with Alzheimer's disease. It's when growth hormone is released in its largest daily pulse, driving tissue repair, muscle synthesis, and fat metabolism. It's when the immune system performs much of its regulatory work, and it's when the brain downscales synaptic connections, pruning and consolidating the day's learning so that the most important things are retained and unnecessary neural noise is cleared. A 2025 study from UC Berkeley identified the specific circuit connecting deep sleep to growth hormone release, finding that GHRH neurons in the hypothalamus activate during slow-wave sleep, suppressing the somatostatin neurons that would otherwise inhibit growth hormone. This isn't happening during light sleep. It isn't happening during REM. It's specifically tied to the deep stages that the VLPO's strong inhibitory dominance makes possible. And there's a feedback loop here that adds another layer. Growth hormone released during deep sleep feeds back to the locus ceruleus, a brainstem region that drives arousal and attention, and helps regulate the waking state the following morning. Deep sleep doesn't just restore the body. Through this hormonal feedback, it actively shapes the quality of consciousness you'll have the next day. Every layer of this system depends on the VLPO successfully holding the flip-flop on the sleep side long enough and deeply enough to complete these processes. Which is why the things disrupting the switch aren't just annoying sleep quality problems. They are interference with a restoration system your brain and body run every single night. When the switch weakens, aging and what to do. There is one honest caveat in all of this that deserves direct acknowledgement. VLPO neurons decline with age. Research shows that the number of functional galanin-expressing neurons in the VLPO decreases progressively across adulthood, and this loss correlates directly with the sleep changes most people attribute to just getting older: more awakenings, less deep sleep, earlier morning waking, and a more fragile sleep architecture that environmental noise or minor stress can disrupt. This is not inevitable destiny, but it is a real biological trajectory. And it means that as the sleep side of the flip-flop becomes inherently weaker, everything on the other side of the equation becomes more important. The circadian alignment has to be tighter. The thermal conditions have to be more carefully managed. The late evening arousal inputs, light, food, stimulation, have less margin for error than they did at 25. This is partly why the same behaviors that produce adequate sleep in young adults start producing poor sleep in middle age, not because the habits have gotten worse, but because the system has less reserve to absorb the interference. The solution isn't resignation, it's precision. Practical protocol, working with the switch. Given everything we've covered, here's how to systematically remove the interference that prevents your sleep switch from doing its job. Start with light. Morning outdoor exposure within 30 to 60 minutes of waking, even 5 to 10 minutes on a clear day, anchors your circadian clock and sets the hormonal sequence for the night. In the evening, dim the environment as sunset approaches. Warm, orange-toned lighting instead of overhead LEDs. Screens dimmed and filtered, or better, set aside an hour before bed. Blackout curtains or a sleep mask to keep the room dark through the night. This is the highest leverage intervention in the entire system because it directly resets the master clock that governs when the VLPO fires. Then address meal timing.
Make it a consistent habit to finish eating at least 2 to 3 hours before sleep. This isn't about the specific foods, though high glycemic eating late makes things worse. It's about the thermal and hormonal interference that digestion creates. 3 hours gives the body time to clear the digestive activation before sleep begins. Then address the sleep environment. Cool room in the 15 to 19 Celsius range. A warm bath or shower 90 minutes beforehand to accelerate the core temperature drop. Attention to sleep position and spinal alignment to remove the microarousal pattern that mechanical stress creates overnight. None of these changes require a supplement. None require a wearable or a special product. They are environmental and behavioral adjustments that remove specific interferences from a system your brain already has, a system that is genuinely designed to produce deep, restorative sleep, and let it do what it was built to do. Most people who implement these changes consistently report meaningful differences within 1 to 2 weeks, not because something new is being added to the system, because something that was blocking it has been removed.
When the switch weakens, aging and what to do.
One final note, because it matters. If you implement all of this consistently, the light, the meal timing, the thermal management, the sleep environment, and you're still lying awake for extended periods, still waking repeatedly, still feeling unrested despite adequate time in bed, that pattern is worth investigating clinically. Chronic insomnia that persists through proper sleep hygiene often involves a specific state of physiological hyperarousal, where the orexin system and related arousal circuits maintain a level of activation that overrides the VLPO's signals. Cognitive behavioral therapy for insomnia, CBT-I, is the gold standard first-line clinical treatment for this, and it works directly on the behavioral and cognitive patterns that maintain that chronic arousal state. Obstructive sleep apnea is another root cause that environmental changes alone cannot fix, and its symptoms are nearly indistinguishable from insomnia to the person experiencing it. If excessive daytime sleepiness, snoring, or waking unrefreshed despite hours in bed is part of your picture, a sleep study is worth pursuing before assuming the problem is purely behavioral. The switch is real. The system works. But it works within a biological environment, and sometimes that environment has a problem that needs more than a darkened room and an earlier dinner. Your brain is not trying to keep you awake. Somewhere in your hypothalamus, a cluster of neurons is trying to flip the switch every single night, releasing the same GABA and galanin that Harvard researchers harnessed with a laser to put mice into immediate deep sleep. What most people don't know is how much they're inadvertently working against it. The light at 10 p.m., the late dinner, the warm room, the mechanical stress that produces microarousals they'll never consciously remember. Remove the interference, and the switch does its job. That's all it needed. If this kind of content, real neuroscience explained clearly, applied practically, is what you want more of, subscribe and stick around. There's a lot more where this came from.